I'm going to be presenting mainly one of the recent work I've done here in Samsung AI with other collaborators about federated supernetworks. And later at the end, I think I'll have time to talk about just two small, but ways I like to work when I do simulation with Flower, which I think is quite interesting. Okay, so first, I would like to spend a couple of slides just doing a recap on how federated learning works. So we are at the same point and we understand what the problem we are addressing is. So in FL, normally there is a central and we have different users. Each of them, they own their own data and the data stays with the clients, right? At the beginning of a round, the server will sample some clients, not all of them. And the server will communicate the model we are trying to train in a federated manner. So these clients will do some local training, maybe a few epochs, or maybe just one. After they send their locally updated models back to the server aggregates them, and a new global model state is generated. And we repeat this process for a number of rounds, which is hyperparameter. But this is a very simple view of the federated learning process, because in reality, every user has its own data. Some users have different data. In this case of this user, it has a high-end phone. Other users might have like a lower-end phone and use many other devices, so they generate more data. Other users might use a completely different set of devices, in this case, like smart appliances, and generate even more data. And we can start to see here some elements that are heterogeneous. Like, for example, we have data heterogeneity. Data is different from different modalities, maybe different amounts. And we see as well system heterogeneity, right? Like if my models are going to be trained on each person's device, we can see that we have devices that are very capable, like the smartphone, on very compute constrained, for example, earbuds or a smartwatch. So these are the two big challenges that almost all cross-device federated learning pipelines have to deal with, especially if they want to deploy them for real. So what does it mean to have system heterogeneity? So it means that we have devices with different capabilities, maybe from different generations. And if we don't handle this properly, we can have some devices slowing down the process. Because, for example, if we are doing synchronous FL, some devices might take much longer than others to finish their round. If we have different type of data, this might create, like some devices might not have all the classes in our data set, or maybe there are big distribution shifts, because even if the same labels are present in all people's local data, maybe they are slightly different. For example, you can think of self-driving cars, for example. When you attach a camera in front of your car, all the images or frames you would extract look kind of different, kind of similar, but some of them are taken in the night and others during the day. So that's a distribution shift we can handle. But in the work I'm going to be talking about, we primarily focus on the first problem, which is addressing the system level heterogeneity that arises when you have very different devices. And this is a work, this work results in a framework and was developed by two amazing researchers here at Samsung AI, Stefanos Laskaridis and Lucas Dudziak. As we have seen in the same federated learning round, we have devices from different capabilities, right? We have high-end phones, and what does it mean to be a high-end phone? So you have a lot of memory, you can process a given workload relatively fast, you have different type of hardware, like you have maybe even an NPU. When we are talking about maybe mid-tier devices, one good example could be a Raspberry Pi, which has an average amount of memory, maybe 4 gigabytes, but is slower in general. And even though it has a GPU, it's a very modest GPU. And on the other side of the spectrum, we have microcontrollers. which almost have no memory. For example, they might have less than 1 megabyte of memory. They have very small throughput, so every model will have a hard time to run very fast. And usually they are even single-threaded. So you can only run workload, and that has to be super well optimized for that particular hardware. And basically throughout the years, we have been able to very well design network architectures that are very well suited to all this type of hardware. And we know how to do it very well for different applications, even microcontrollers. But then the problem is that if we want to federate these very different models, for example, they send the update to the server, we know that these models are so different that we cannot just take an average of them, right? We have layers have different shapes, tensors have different shapes. If you try to do the addition, well, it's gonna result in an error. There are workarounds to handle this in the server. For example, you can do distillation, there are other techniques, but those also make of other assumptions. Like, for example, you have another data set in the server that you can use for distillation, which might not be possible in all cases. So in our solution involves creating a supernet. And what I'm gonna do now is to explain a bit what a supernet is and why it is indeed a good solution. So a supernet, you can think of it to be like a regular neural network, but every node you see here, instead of being just one weight, it represents one type of layer. For example, each of these dots will be different type of layer that might have different footprints. For example, depth-wise layer might have very few parameters in comparison with a, for example, 5x5 layer. And all these different layers, when you stack them together, you build a supernet. And the way to extract a standard model out of the supernet is by sampling one operator in every layer of your supernet. So for example, if I have a high-end phone, I can afford sampling very computational and memory intensive layers. So I would sample, as you can see here, the red path. And if I extract that results on the model you see right under the phone. If, on the other hand, I have a very constrained device, like the microcontroller, I can sample other paths, and it will result on which is the green path, and it will result in a much smaller model. What's the benefit of this setting instead of having completely independent and isolated models, as we saw before? Well, the difference now is that every device participating in FL will receive the supernet, and they can decide which path to sample. And depending on the path they sample, they will update those weights, but still those weights are embedded in this model, which is a supernet that is common to every device, regardless of the capabilities of the device. And because every device is sending back this big supernet, there is no problem of shape mismatch in the tensors. So you can proceed with your, for example, your regular strategies like Fed average, or you can propose your own, which is what we did, as we'll see next, to better handle the unique aspects that happen when you work with a supernet. So with the supernet, we have fixed the problem of aggregating, which is one of the big limitations you couldn't do before. And what I'm going to show now is what are the main stages in the Federated pipeline that enables the learning of the supernet in a federated fashion. So the supernet is like our global model that lives in the server, and we initialize it randomly, like you can do with Flower. And then at the beginning of every training, of every round, what we do is, instead of sending supernet, which can be very, very big, we sample this supernet. And we sample it based on a budget, a communication budget. And we say, for example, I want my sampled supernet to be less than 20 million parameters, for example. So only some of the operators in every layer will be sent to the clients. For example, in this diagram above, we have two clients. One is a Raspberry Pi, one a microcontroller. And you can see they receive a supernet, but some of the paths are like with a dashed line. That means that we didn't communicate that operator because we wanted to save on communication costs. But still, the clients still have a sub-supernet that they can sample based on their compute capabilities. And because the clients themselves know what are their budget, for example, a Raspberry Pi will have a higher budget than a microcontroller, they take samples accordingly. And the way we implement it is that for every batch of training, the client will one path randomly. So over the course of several local epochs, we can guarantee that there is a fair good coverage of all the coverage of all the paths that can be sampled by that client. And then, well, the locally updated supernets are sent back to the server. Here, we make a slight modification to Fed average, and instead of in the average of every operator in every layer of the supernet, we keep track of which ones have been sampled in order to weight them accordingly. Because, for example, if the microcontroller here is super constrained, it might only be sampling, let's say, one operator in the layer all the time. So we might want to give it more weight to that update than to another operator that might be sampled only once. And once after aggregation, everything is used to update the global supernet that is still in the server, and the round ends, and we continue with the next round. This, which is like the main contribution of our work, is just one of the stages in our pipeline. And why do we need other stages? One of the reasons is because we are working with a supernet. And in this supernet, for example, for ResNet 18, the moment we have, you can imagine 7 operators per layer, and we have maybe 10 or 16 layers, you end up with many, many paths. Every path represents some model. So we need to search for the best models in the supernet. And these models, the good thing is that they are already pre-trained because we have been training this supernet. So in stage 2, we do the search in a per tier fashion. So we say, okay, which is the best path that has this particular footprint, for example, more than 500 megaflops, but less than one gigaflop. So we sample of those, we take the best, and we say, okay, this is the model for a high-end device. And we repeat the same for other tiers. Extract this path. This can be treated in a normal federated learning setting, where there is only one model that only devices of that tier can keep training, for example. And that's what we presented in Fedoras, which is the current state of the art for tier-aware federated learning. One of the big benefits we have here is that because there is this knowledge sharing happening through the supernet, very constrained devices can still benefit from the higher quality training done by higher capacity clients or more powerful clients. And the other way around. Normally, maybe you have only very few very powerful clients, but many, many very constrained clients. So as we will see in the next diagram, that's also a big problem, because if very powerful clients, there are very few powerful clients, they might not be able to have enough data to train a model that is as good as you would expect from a device of that capability. And that's what we're going to see in this diagram. So here what I have represents different models, and the x-axis represents computational footprint. So the bigger the computational footprint, which is measured here in flops, you would expect the better the performance of the model. So bigger models will be towards the right of the plot, and they do perform better than those that are towards the left, which are more constrained. So when all models can be trained on all clients, this holds. You can see that a bigger model works better. But the reality is that maybe bigger models cannot be trained everywhere. For example, here, models that are tier 4, we say that can only be trained on 25% of the clients. Because of this, these models are only exposed to 25% of the data. So they perform very poorly compared to much smaller models that have access to, that can be trained in all clients. And we call this the client participation gap that we can solve with Fedoras thanks to the SuperNet, because even though some paths in our SuperNet can only be trained by big clients, those same operators might have already also been updated by other clients, much smaller. So in the end, everything in SuperNet has the possibility of being updated by all clients. And I think that's what I wanted to share about Fedoras.